selection rule number 2 says that the rotating molecule can increase or decrease its rotational energy only to its either next higher or next lower energy level. That means it can either go to the next higher energy level or it can come back to the next lower energy level, depending upon whether it is absorbing the energy or the molecule is emitting the energy or the quantum of energy. In other words, it can be interpreted as the transitions are equispaced with spacing of 2b. Now, what does this mean actually? Let's try to understand this. We have already known from our previous video that the Ej is equal to B times J into J plus 1. And we have also mentioned over there also that actually if the molecule is the same, then the value of B remains constant. Why? Because the moment of inertia remains constant, and then in that case the energy is totally dependent upon the value of J. Okay, so if we try to calculate the value of energy of this rotating molecule when J is equal to 0, so I write E naught or E0 over here, so it becomes B times 0. That means 0 amount of energy is there. Okay, so and if J is equal to 1, then energy E1 will be equals to B times 1 into 1 plus 1. That means B into 2, or we say energy is equal to 2B. Okay, so if I try to plot this over here, I will simply see as this line where energy is equal to 0, and when does this happen, where J is equal to 0. Now when I try to increase the value of J on this particular graph, J is equal to 1, so my energy of this rotating molecule becomes equals to 2B. Okay, similarly if the value of J is 2, so E2 will be what? B times 2 into 2 plus 1, so E2 will be equals to 2B into 3. That comes out to be 6B. So the value of energy where J is equal to 2, this is equal to J is equal to 2 level, where the energy will be 6B. Okay, likewise we can calculate the different amounts of energy when J is equal to, let's say, 3, or further moving upwards when the value of J increases to 4. So when J is equal to 3, the amount of energy comes out to be 12B, and when J is equal to 4, it comes out to be 20B. So with an increase in the value of J upwards, the value of energy is also increasing. This further simplifies the fact that actually energy here is totally dependent on the value of J. And also the second thing that we come to know from here is that the energy carries a particular amount of energy, multiple of B, and that is having a specific value. When J is equal to 1, it is 2B, it increases to 6B, 12B or 20B. That means energy here is quantized. So the energy of the rotating molecule actually is quantized. So if somebody asks that, okay fine, can the energy value of the rotating molecule be equal to, let's say, 10B, so this is the wrong answer. It cannot be equal to 10B, it cannot be 11B, it cannot be 9B, and it cannot be 5B, and so on and so forth. The energy cannot be equal to these terms. Why? Because it is having a specific multiple value of B, that is 2B, 6B, 12B, 20B, 30B, 42B, and likewise it goes. So the energy is increasing upwards as we are going. Right, now if I want to calculate the change in energy, that means if I want to refer it as delta E, so delta E will be equal to what? Delta E, if let's say the J value is increasing from, let's say the J value is increasing from 0 to 1, so delta E from 0 to 1 will be equal to the energy of this molecule when J is equal to 1, okay, that means 2B, okay, minus the initial energy, that means when J is equal to 0, which is 0. So your delta E with respect to when J value changes from 0 to 1, it is nothing else but 2B. So this amount of energy, this delta E value, this is equal to 2B. Okay, so this is 2b, your delta E. Now these are the delta E values from 0 to 1. Okay, if we try to calculate the change in energy from 1 to 2 when the J value is increasing from 1 to 2, so what will be my final energy, which will be 6b. Okay, when it is having the J value as 2, minus when the value of J is 1, the corresponding energy is 2b. Okay, so that comes out to be 4b. Okay, so from 1 to 2, when it goes on, the change in energy, this much amount of energy is 4b. Okay, likewise we can calculate all the change in energy or the difference in energy in the two respective and consecutive levels of J, and here it will be 6b and so on and so forth. So from this change in energy, one thing is made very clear. If you try to make out the difference between these two, it is 2b. Again, the difference between 2 is 2b. So this is what the statement of the selection rule means over here, that the transitions are equispaced with spacing of 2b. So everywhere it is 2b spacing. These spacings are of 2b. So it is consistent in that case. It remains consistent in that case, and it is 2b. Okay, so we get the spectrum like this. If we try to see the spectrum, actually we get it like this. This is our absorbance, okay, on the y-axis, and my spectrum will be like this. Okay, and your 2b, okay, and your 4b, and your 6b, and your 12b peak will be here. Okay, so this will be the spectrum, how it looks like when we plot it. Okay, so these are the two selection rules specifically. I hope the selection rules are very much clear to you as far as your microwave spectroscopy is concerned, because actually these selection rules are a way towards the movement of the calculation of energy and understanding the spectrum and what information it gives to us. So these two selection rules are important as far as microwave spectroscopy is concerned.